Oh, you need to put it back up.
I know. Okay, so now that you guys are writing a fair bit of C++, right? So,
Oh yeah.
You guys realize that there are these crazy books that say stuff like this. Teach yourself C++ in 21 days. And now maybe you can appreciate, you know, this cartoon a little bit more. And we can say the same thing about other languages as well. I mean, actually learning how to program is not syntax. It's a whole bunch of different things. So, everybody good? I guess it's not that funny. It's a little bloody, I guess, in the end.
I thought it was great, Peter.
So, this one is also so Richard's Guide to Software Development. This is how like software projects actually happen.
Hold up. I need to look.
Yeah, that was a little more funny.
Wait. How much time has to be spent?
I'll just register them all for compilers and then show them the first comic you go.
Oh, I still like
They'll learn to laugh.
wholesome memes.
Anything compilers teach you how to be happy.
I went looking for these because there was a great question on Piazza, basically, where somebody's trying to use a feature of modern C++ or a later standard of C++, and was having trouble because the C++ compiler doesn't do that standard by default. So anyway, so I think that we don't have like I don't know about these guys, but I don't have like a planned out like a presentation or anything like that for this. I thought we'd run it pretty much like the midterm, the review for the midterm, and basically just go from your questions. So, does anybody want to start, or shall we just kind of walk through the syllabus, kind of briefly, to get a sense of what this exam is going to cover? Why don't we do that? Okay. So you guys are going to have an exam on lecture 18 through the end of class. Okay, so basically, let's think about what was there. So there was basically a week on relational algebra, right? So the various aspects of relational algebra, right? So this is the algebra for making queries, and also, surprisingly, the algebra for making constraints, right? So constraints and queries can be represented within this algebra, basically as combinations of queries are expressions, right? Statements are constraints. I tried to show you guys this very close connection between relational algebra and SQL, right? So it's a little terrifying if you see relational algebra from the get-go, but if you realize that SQL is kind of an implementation of it, and you know a little bit of SQL, then hopefully it's a little bit easier to understand. The parts of it that I find, a little bit challenging, at least when I first learned it, are things like projection and how projection works and how it's different for bags and sets, and then of course the grouping operator, which is a giant, a very complex thing, right? The equivalent is the group by stuff in SQL and aggregation. So I think the rest is relatively straightforward. You guys also had a lot of homework problems on relational algebra, right? That had these various flavors of like, here's a relational algebra expression, right? What is it? Well, here's an example kind of problem you might see on an exam. Here's a relational algebra expression. What does it actually do in English? Here's a relational algebra expression. What does the SQL looks like this? What is the SQL equivalent? Well, here's some SQL. What's the relational algebra? Yeah. Sorry?
Your mic's not on. Huh. No, it's on.
Yeah, I heard
Oh.
it.
Oh, I had it. Sorry.
Oh, there we
Sorry
go.
about that. Okay, so did you guys miss what I just said in the last 5 minutes? Okay. You want me to say it again? Okay. So, this exam is on lectures 18 and on, right? One big topic in there is relational algebra. You guys have a homework. We provide solutions for the homework on this very topic. You can be sure there's going to be questions about relational algebra and its different flavors, its connection to SQL, all these various operators that we talked about and what they mean, the equivalent to, and the SQL equivalents thereof. In my opinion, the ones that let's spend some time understanding are the operators like projection, which works in surprising ways. And by the way, all the operators work differently or can work differently depending on whether you're talking about the relational algebra of bags versus sets. Right? Yeah, so when I was learning this stuff, I found projection to be a challenge to wrap my head around, especially projection for sets. The grouping operator is a big thing, just like group by and aggregate functions are in SQL. So that's an important thing to wrap your head around. We talked briefly about data mining, right? This idea that you can sort of use the grouping operator and aggregation functions and group by in SQL to basically give you probability, to give you statistics, right, from across data, and that's the basis for, those two are the basis for giving you tools for data mining, for finding associations in the data that might be useful to you. So anyway, the big thing about relational algebra is you guys have homework for this. Make sure you do it. The stuff that you're going to see on the exam is going to be simpler than the homework. Okay, so we then went and dove back into SQL, basically trying to bring up some stuff that was not necessary in our initial pass of the first part of class. Right? So what are the big things here? So for sure, you should know what three-value logic is, right? And for sure, you should know the consequences of using nulls, right? And what nulls do, especially with arithmetic involving nulls. You should know what a correlated subquery is. Do I care about all the various aspects of it that the book talks about? Not necessarily. You should know what a correlated subquery is. We went through a lot of detail about things that SQL has, that practical SQL implementations have. Some of them we've used within the portfolio project, things like use, right? Things like the notion of transactions, right? Multiple statement transactions, or that they exist, let's put it that way. We spent a fair bit of time talking about triggers, right? So you should be comfortable with triggers, right? So row level, table level, before, after, instead of, conditions, the events you can trigger on, what the code is that actually manipulates it, right? So I, for example, gave you a trigger expression and said, decode this for me, what is it doing? You should be able to do that. Okay, and then we went into the part of class that unfortunately doesn't really have homework for it. But it does have a project. Project touches on some of the aspects, and that is implementation. So I know that there's a lot of reading here, so I'm going to try not to like do some, ask you some obscure questions in the corner case of the reading, but I do want you to have done the reading. Okay? You for sure should know what B-tree indexes are doing, right? Should have that backward and forward. And if I ask you to sort of generalize a B-tree index, to basically create a B-tree index with some additional features, right? You should be able to think, oh yeah, I can see how I can fit that in. We didn't spend, obviously you didn't do implementation, but you guys have also been exposed to hashes. Remember, hashes, a big thing there is basically how to grow and shrink them, extensible versus linear hashing, what do those mean, and what are the differences, what are the advantages and disadvantages. Bitmaps, right, what those are. You should also kind of know, for indexes you should know what are all the big O's, right? So what is the actual cost of searching for something with an index? So we didn't really give homework for this, but like one question I might ask is something like, well, here's this table and here's a select statement. How do you make that select statement fast? How fast can you make it? You're allowed to make any indexes you want. How do you make that select statement fast? And remember, one of the select statements that we spent a fair bit of time on, once we learned B-tree and hashes, was hash join. Right? How you can make a join nice and fast. Yeah.
Since we haven't had a chance to practice on the later material, but the textbook does have exercises on it, but then we can't check if we got the material right. Would it be possible for you to publish like answer keys for some of those practice problems?
For the exercises in the textbook,
Yeah.
I can't do that. I'm sorry. I do encourage you to do the answers. I mean, basically, I don't have the exercise answers.
There was an online, like the writer of the textbook has a thing online
Okay.
that he published, which has answers.
Shall we look that up?
Yeah, I think it's like Stanford Ullman. Yeah, that's the name.
Okay. That's your time. Solutions to selected exercises?
That, and also there's like a online testing thing, like where it's like multiple choice, and then you can also practice secret queries. Also.
Okay, so what are we going to look at here? So online solutions. So if we're looking at chapter 17, there are solutions for some of them, right? Is what we're saying?
No, there's like an actual, he has like a whole testing suite where you can test yourself on how to do it.
Okay.
I can find it.
Yeah.
Yeah.
Post it on the outside.
Yeah.
Yeah.
That was my next one.
Yeah, I can do that.
Okay.
Yay.
So I will say that like for a lot of the systems aspects, kinds of questions, for an exam, they almost have to be about like what they allow you to do, right? So, for example, if I said, if I gave you a select statement, which was a range query, like what index should pop into your head? B-tree. What kind of B-tree? B plus tree, right? If I said something was just, look for last name equal Jones, right? What should pop into your head? Hashes, right? If I said something like intermediate result, like we want to basically get a return value from a part of the query, right? That is a subset of the records, a subset of the rows that match. One thing should pop into your head is bid map. Okay. Yeah, and then for transactions, again, we're still covering this in class, but I do want you to know, like what are the two main things that transactions are built on, right? Logging and locking. I want you to have some sense, and I know we haven't covered this in lecture yet, but I want you to have some sense of what these scheduling mechanisms, scheduling ideas are. Serial schedule, serializable schedule, conflict serializable, two-phase locking, etc. Logging, right? We did redo, undo, and when you ask a question about something like logging in an exam, it's really often it's going to look at the trade-off, right? So a lot of what is in a system at systems level that you can actually ask a coherent short question about has to do with trade-offs. Right, like what is an undo log good for as opposed to a redo log? And what is a redo log good for as opposed to an undo log? Okay, so, right, so that's the broad shape lit, right? Relational algebra, advanced SQL, implementation, systems. Okay, so, somebody like to kick us off with a question?
Yeah, I
Yes. I think I posted about this, but in case I haven't, I will. You're gonna have the same sort of single page cheat sheet as for the first exam. Also, the formatted exam is gonna be very similar, right? So it's gonna have a 20 true false questions, 30% short answer, and then 50% in depth. I mean, I'm not done with this yet, but probably it's gonna be 20, 5, and then 3, just like the previous exam. So 20 true false, 5 short answer, 3 in depth. And also some of the in depth, I will say that for this type of exam, I can ask you kind of an obvious in depth kind of question, right? Like I mentioned before. Here's some SQL. Tell me what the relational algebra is. Here's the relational algebra. Tell me what the SQL is. Are these two relational algebra expressions equivalent or not? Like when you reduce one to the other. Those things are easy kinds of questions to write. What's another kind of flavor that will show up here? Indexes, right? Here's a table. Here's a bunch of queries. How do you make these fast? Or here's a table. Here's a bunch of queries and a bunch of indexes. How fast can these go? Right? And like big O terms. But there can also be like thought experiments. Okay, so I'll ask you one. So I mentioned this to several of you folks before, so I might as well mention it to everybody. Have you guys heard this term splay tree?
It's like a self-readjusting tree.
It is. If you know what it is, don't pipe up right away. So a splay tree is a balanced binary search tree. Okay, you could imagine generalizing it to be k-ary, to make it better for a disk. But just think balanced binary search tree. But it's a binary search tree where you balance it not only when you insert, update, or delete, but also when you look up. So when you do a lookup, a balancing operation happens, which pushes the thing that you just looked up closer to the top of the tree. Okay, so it's not a tree where all the values are at the bottom. It's a tree where the keys and values are distributed across. It's a tree where the keys and values are distributed across the tree. Oh, and by the way, it's allowed to unbalance itself. But the overall principle is kind of like the rotations you may have learned about from red-black trees. Like you do an insert, some rotation happens to balance or change it, right? And sometimes but the key thing here is that when you do a lookup, the only things you're doing are lookups. These operations happen that pull the value you're looking at closer to the top of the tree. Okay, so here's my question. Let's see. Here's my question. Why would I want to do this?
If you were doing like a Huffman encoding or something like that.
Louder.
If you were doing like a Huffman encoding.
Okay.
Something like that.
So you're on the right track. Huffman encoding is motivated in a kind of similar way. Somebody else. Make a flying guess. Somebody doesn't usually raise their hands. Come on. Okay, somebody likes to raise their hand.
It has good temporal locality because the things at the top of the tree are more likely to be in the cache because like you're using the root a lot, you're using the second layer a lot. And then if you move something you just access up, then the next thing you're going to see it might already be in the cache.
So that is a good answer. And if you wrote that, it's not the answer I'm looking for, but if you wrote that on an exam, I'd be like, oh, that's a good answer too. Good. Okay. So suppose we didn't have a cache at all. Why would it still be interesting?
If, like, for a particular problem, some keys are much more common than others, you can get access to those keys really, really quickly compared to, like, unusual insertions.
Yeah, so basically, it's getting at the idea that keys are not equally popular. Right, so imagine that you're building this thing over last names, right? There are last names that are going to be much more commonly searched for than others, right? I mean, not to beat a dead horse, but Smith is probably more likely to be searched for than Dindal, right? And so what'll happen to the Smiths? Keep searching Smith, 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 and this data structure is going to move the Smiths up closer to the top, right? Why is that good, even if we don't have cache?
It's like less blocks to search through to like access. So stuff that you access more often is gonna take less block accesses.
Yep. So that's true even if it's in main memory, right? So the popular stuff is going to be at the top of the tree, and so the searches you do, right? If you're searching for a popular thing, you're going to have to follow a shorter path to get it. And so it basically optimizes the tree based on popularity. Whereas something like a B tree, it optimizes the tree so everybody's search is all searches are the same length. This one, the searches are uneven length, right? But the ones you're searching most often for will be shorter. And the ones that are less often are going to be longer. And there's a good comment, right, about Huffman encoding, which which may or may not be familiar to some of you, but basically it's kind of a similar idea for encoding symbols. So you basically can make symbols that are very common, very short, few number of bits, at the expense of making uncommon symbols that you're trying to represent require more bits. So for example, you might represent Smith instead of S-M-I-T-H, right? All those bits you might represent it with 5 bits, and that's Smith, that's common. Whereas Dinda might be 300 bits. It's very uncommon.
What if you had a data set where everyone was accessing for
Okay, that's a good question. So I have a splay tree, and it's uniform popularity among all the keys. Is it a good idea then? So somebody's shaking their head no, want to say why?
If you're gonna rebalance the tree a lot, which is useless, so you might as well just use a different data structure for each tree, so you have other aspects that are quicker.
Right, so you're doing all this rotations, all this work on the data structure that is never going to actually benefit you because everything's equally popular. Okay, so this is a flavor of a question that I could bring up for talking about indexes or data structures in general. It's just like it's a thought experiment. Okay, other questions? Yes.
Can you talk more about what bitmaps are like?
Say again?
Can you talk more about what bitmaps are like better?
Okay. So first of all, bitmap can be a very compact representation of a set. So independent of whether we're using it to index something, it can be very useful as an intermediate representation, right? So you have, your table has 1,000,000 rows, you have 1,000,000 on the bit vector, and every place where the bit is on at that index, that corresponding row is in the set. So it's a representation of a set, basically, in a very compact way, right? So that's one of those really useful things, right? So just make sure you have this picture in your head where it's like, if I have bit position I and it's set to 1, that implies row I is in the set. Okay? And the other thing that this buys you is that you can basically do simple set operations. They flatten into very simple binary operations. So what is a set intersection? Somebody else. So I have a set that's represented by one of these bit vectors. The bits corresponding to the rows that are in the set are lit up to 1. And now I have two such sets, two such bit vectors. And I want to do an intersection of those two sets. What do I do?
Logical and.
Yeah. Well, logical? So logical and, you may be thinking like C's logical and, like ampersand, ampersand.
Right.
So, well, you want actually one ampersand, which is the C bitwise and, right? Which basically means you have two bit vectors, and it computes this and that to generate an output bit, and it does that and that at the same time to generate the next output bit. So it's bit by bit. If each bit here is AND with the corresponding bit here to generate the output bit there. Okay? So if you do that, intersection turns into bitwise and union turns into bitwise or. What does not correspond to? Bitwise not. So if I do bitwise not, the set, that's basically like saying take the full set, make the set of all, and subtract the set. Right? Because you're basically saying, tell me about all the things that are not in this set. Okay, and the other thing is that the operations, like you have a complicated query, and you're basically saying things like, I want, last name to be Smith, and I want address to be Evanston, or I want last name to be Jones and address to be Chicago, right? That sort of thing where it's like, in the query itself, you're doing ands and ors and nots to construct a set of things, to construct a query, to construct a filter expression. Those ands and nots and ors in your own query, right, in your own SQL, can turn into these operations as well. So if I say, this is, for example, the bit vector which is all of Jones, and this is the bit vector that's all of Chicago, if I intersect those, if I AND them together, I'm getting, name is Jones and city of Chicago. So it literally turns, the AND in the query literally turns into the bitwise AND here, which corresponds to the intersection. So those are the sorts of things that bit vectors are very good at. You can do some other clever things with bit vectors. So for example, you can do partial queries. So if you're looking for like a stem of a word or something like that, there are ways of building that as well, which the book will talk more about. I think the last thing I should mention here is that this type of index, it's not, the bit vector is not the index in and of itself. That's just the representation of the set that has some property. So we also typically want to have the properties pulled out as well. So the property we care about in the previous example is name equal Jones, or we care about the property name. And so we can imagine that we have a set for every possible name we have one of these bit vectors, which tells us the set of records, the set of rows, where that name exists, right? Where Jones exists, or Smith exists, etc. And then you can introduce another concept, which is that like indexes are not, they don't have to be like a singular thing. It's not necessarily just key takes me to data. It can be key takes me to another index, which takes me to data. So for example, I might have a B tree index of all the unique names. Okay, and I look in that index for Jones. And that index takes Jones and it maps me to the bit vector. And then I can use that bit vector to basically as an intermediate result for doing things like name equal Jones and city equal Chicago.
I remember we talked about this.
Does that answer your question? Okay.
But, so like, what are the strategies for like reducing the size of the bit vector again, for when you don't want to represent like every.
Yeah, look, I mean, so that's kind of a little bit of a sidelight I did in lecture. So I talked about information theory and I talked about compact representations of bit vectors and whatnot. So that's not in the book and it's not going to be on the exam. Okay, so first of all. And then to answer your question, I'm just saying, the reason why I went and talked about that is because when you first read about stuff like this, it seems like an insane thing, right? That you'd have a bit for every record, and you have a bit vector for every possible value that something can take on. It seems like an insane amount of space, and it also seems like it would take an insane amount of time, right? So when I say stuff like, let's do a bitwise AND to have some intersection, that looks like big O n, right? Because we're going to look at n bits, and because we can come up with more compact representations for common cases, it's usually that the worst case is big O n, but usually it's much smaller than that. So as a practical matter, it tends to work. And in class, I was trying to give you a sense of where the limits might be for that. Right, so essentially, you can kind of say the more compressible that bit vector is, right, the less information that's actually stored in it, and not only will it take less space to store it because of compression, but also it takes less time to compute over it. Right, and a funny thing when you talk about systems aspects of things is that usually you have choices between like a thing which is, you'll have choices where either it looks like the big O is the same between two things, or in which case the constant matters extremely, and you might have a different choice depending on how big n is. Like so constant typically for one kind of thing will dominate when n is small, and it will work differently when n is big. But also you can have cases where it's like you have big O n algorithm like bit vector, and you have log n algorithm like B tree. And you think, well, of course, I don't want the log n algorithm. But a lot of times the constant matters so much in a practical system that you might choose the theoretically wrong option, just because you want, as a practical matter for that instance, it will go faster. Okay. Other questions? Yes.
Could you potentially go over some relational algebra examples, like maybe some of the ones from homework or something?
Sure. Shall we pick one?
Oh, you can actually raise it from, that's, Mike, how do you raise it from the touch screen?
Oh, I just powered it on.
Oh, and normally the screen, okay. Never mind, can't do that. Oh, then it drops. Okay.
Yeah. So we could also just look at the, we could look at some solution sets, if that would help. All right, so I'm not, so the book spends a lot of, the book questions have a lot of the flavor of like, how do you ask a particular question, right? Like, they're like, here's this query in English, go figure out how to actually ask it in relational algebra or SQL, okay? So I'm not going, in the exam, I'm not gonna ask you a question like that, okay? I'm going to ask you a question like, here's some SQL, tell me the relational algebra. Here's some relational algebra, tell me the SQL. Here's some relational algebra, tell me what it means. And what you're actually searching for. So,
And when you say like, tell me what it means, does that mean like, say what it is in English? Like,
yeah, exactly.
that's in the book.
That's exactly. But I'm not.
But
What I'm not going to do is I'm not going to, like, the book is basically trying to force you to think about how to ask increasingly complex questions using SQL or relational algebra, which is very hard in an exam to do. And that's kind of why I gave you the homework, and also why you had to answer. Like, some of you guys, I know for extra credit, I mean, I just graded some extra credit just before I came here, where it was like 5 lines of SQL, 5 screen lines of SQL to figure out kind of a cool portfolio measurement, right? So I think you guys have engaged with that part a lot. Like, I want to do this particular thing. How do I cast it with the SQL? Does somebody want to like just give me a select statement? Okay, actually, before somebody gives me a select statement, just meta question or higher level question. What is a constraint in relational algebra? What does it correspond to in relational algebra? So query is an expression. Constraint is a louder statement. Okay. What is the only statement I really need?
Really equals the empty set.
Yeah. The expression equal empty set is the only statement you really need to write a wide variety of constraints, functional dependencies, keys, etc., right? So that's why we're really going to, the focus really should be on the expressions. Because once you have those, the constraints are just different things. So, all right, actually, I got a question for you guys. So somebody tell me a query from your portfolio project, right? They're all graded, they're all, you have all the grades back, so it's all fair game, right? You don't have to worry about it. So somebody give me a query, like how did you find, well, somebody give me a query from there. So if I said something like, So if I said something like that, how do I convert that? Let's convert this into a relational operator. Okay, does that seem like fair game?
Select symbol, standard deviation last. From SD, where timestamp is less
So when
than
I approach these things,
1,
I approach them by drawing a picture.
8,
Right?
group by
So my first
symbol.
thing is to say, what is my input to this select statement? Right, so what is going to flow into my expression? So stocks daily, right? And actually, I'm going to write it a little bit different. I'm going to say stocks daily, but I'm going to call it SV for whatever reason. And I'm going to call standard deviation of last as just going to call it S. Okay, just add some more stuff to it. Okay, so we have stocks daily. And what am I doing to it first? Sorry?
Renaming.
I'm reading it, but what is the first operation I'm doing to it?
Renaming is what she said.
Yeah, I know you know.
No, she said that.
Oh, I'm sorry. My bad. Okay, so we're renaming it, right? We're gonna call it SD, right? So it's a row. Okay, what happens next?
Select value for timestamp is less than 1 million.
So select timestamp. Basically, is it old? Okay. And what happens next? Somebody else? Okay, well, what do we have left? So we have this. This is a projection, right? And we've got this, which is a group by. And group by is a little bit goofy because group by, right, in SQL you sort of think, oh, here's part of it here, and here's part of it there, right? So what do you think is happening first, the group by or the renaming? Or sorry, the group by or the projection? Okay, somebody else have a theory? Project or group by? Okay, and we're going to say it's group by, right? So it's going to go into that weird gamma thing, right? So what are the parts of the group by? So when I say gamma, what is the sub? What are the attributes I have to have here? So I have to explain how I'm doing the grouping, right? So what attributes define the grouping? So what attributes define the grouping? Symbol. Okay. Any other attributes? Remember, you can have more than one. Okay. So this one only has one. All right. What's the other part I have to have? I have grouping attributes, and I have I'm going to group, and then I'm going to collapse the groups down into single values. So to collapse the groups into single values, I need a aggregation functions, right? So what's the aggregation function here? So remember, when we write in SQL, it's a bit weird. So the grouping attributes are down here, and then the group by is up here somewhere. Or the aggregation function is up here somewhere. So what do we think the aggregation function is? Remember, you ran into some of these like count, average,
Standard deviation.
standard deviation. Okay? standard deviation of the last column. Okay? And then the last thing, then we're going to do the projection. And we're going to project out symbol. Well, in this particular instance, we don't have anything left, but basically we're going to project out symbol and this column, which is now called standard deviation last, and we're going to rename it. So we're going to call this thing S. And that's our output. Okay? And so if I can draw this, then writing it becomes a lot easier, right? So if I want to write it down, it's like select symbol SD last. Sorry for my handwriting. Of gamma symbol SD last of selection timestamp less than 1 billion of renaming, let's call it SD of stock scale. We add enough parentheses. So really, at least to my mind, if I diagram it out, like if I just show the flow, write down the flow. Because remember, an expression is just a tree. All expressions are going to be trees. So you will be able to draw something, and then you can take that drawing and you can write it down as it's, this sort of linear expression if you want to. Okay, so what if I did, let's try another one. Let's do the opposite. How about if I tell you, okay, so somebody walk me through relational algebra for that. So select last name, latitude, longitude from candidate master, right? They go to the first lab, natural join candidate ID to geo as CM, where the state is equal to Illinois and the last name is equal to Jones. I'm not sure how much I'm helping you at this point, so please stop me if I'm not. You know, but like what would be the equivalent of something like this? It would look like we have candidate master, right? And we have committee candidate ID Geo. And they're flowing into a natural join. We're taking the output of the natural join, we're renaming it. So then we are doing a selection. So then what are we doing? So we're doing a projection. To give us last name, latitude and longitude. Okay, and I could equally well show you this and say, develop that. Okay? So now there's the question of what in English is this query doing? Out of those forms.
It's getting every candidate in like the geographic location where they live, as long as their last name is Jones and they live in the state.
Yeah, so find me all the, exactly, so find me all the Illinois, Joneses, locations. Find me all the candidates in Illinois, whose last name is Jones, and their locations. Yeah.
When the reader is actually implementing this query, would you want to do the like select before the join, or would it do it this way?
So that's a good question. So let me give you a different version of it. Suppose I said, you get that relational algebra, and I say there's another kind of relational algebra that looks like this. And I am doing, I'm going to do that state selection and the last name. So then I'm going to take that and run it into my natural join, and then into my projection. Okay? So all I'm doing is I'm doing what you're suggesting. I'm taking this select, and I'm pushing it down past this, and pushing it all the way down here. And here's my question. Are these equivalent? Are they equivalent expressions? Are they two ways of computing the same thing? Who would vote yes? Okay. Who would vote no? Who doesn't want to vote? Okay. So these are equivalent expressions. This I'm pretty sure. I'm making this up on the fly. I'm pretty sure these are equivalent expressions. And to your question, would this one be a smarter way of doing it than this one? Like in terms of the database actually implementing this, is one of these less work than the other? Yes or no? Yes. So one of these is less work than the other. Which one's less work? Left or right? left one. Why?
Because we're doing a natural join plus the
So what's going into this natural join here is only the Illinois Joneses, right? What's going into this natural join here is all the candidates across the entire country, right? So this is going to be, if there's 100,000 candidates, this is a 100,000 step join, right? It's going to generate 100,000 outputs. This one, how many Joneses are there in Illinois? Less than 100,000, right? So this join is going to be a lot cheaper. All right, to tie this to another question, how cheap can I make this join? So think about in terms of systems and in terms of indexes. Right, how cheap can that join be?
Sorry, this is
Yeah.
just a question about that.
Yeah.
Would you do the rename in between the?
Oh, sorry, I lost the rename.
Sure.
Yeah, you're right. I would throw the rename down here. You're right, they're not equivalent without that rename. Or, sorry, actually. I put the rename up here. And then the projection. Yeah.
But if you choose, they are still not equivalent because the CMD and the CMD is different.
Why are they different?
Because that one CM, like the right side CM will have more tuples than left side.
Oh, but the thing is, when we care about, so when we say that two things are equivalent, we mean that we don't care if the subtrees are equivalent. We care only that the end result is the same. We'll compute the same thing. Right, so you're right. So this is, the output of this rename is going to have a lot more tuples than the output of this rename. But we don't care about that. We care about the output of the whole tree.
So if we don't have the rename on the left side, the output will not change. So are they still equivalent?
If we don't have the rename on the left side, I shouldn't be, I don't want to push the rename is for the data after the join. So I push it back down here. The problem is that the data that's going to be appearing out here is going to have a different name.
So now these two are exactly the same. The output have exactly
I'm
the same.
claiming, again, I'm making this up on the fly, okay? So I believe I'm getting this right. So what the main thing that we're doing, the main reason why I brought this up is just, well, two things. One, equivalent expression, useful thing to think about. And equivalent expression, in this case, basically pushing that select. And it's this part that really I care about. Pushing this select down here past this natural join radically changes the amount of work the natural join has to do. So same answer, Robert's work. Independent of how you actually implement the join itself. And then what I'm asking is that if we choose a specific implementation, how fast can we make this happen? Like if we actually were doing the join in a database, and we had B trees and hash tables and bitmap indexes, how fast could that join go?
Just one for one. So
Yeah.
So if the output has to have column names same, right?
Yeah, and the relation name should be the same. Yeah. So the rename basically allows you to change the. So here what I'm doing in shorthand really is I'm basically saying I want to rename the relation. I don't want to change its attribute names, but in general I can change its attribute names as well.
Could it be done in linear time with the number of results?
Okay? How so?
So first, you'd have a hash table for state on the candidate, ID to geo. And you'd also have a hash table on last name for candidate master, so then you kind of get, you get two sets of things.
Okay.
And then if you take this set, you take the set from candidate ID to geo,
So,
from
so
candidate to geo,
yeah.
you take all those results and use like a hash join. And you can make sure that they also satisfy the last name requirement if you have like a bit vector for that set. And then you look up
Okay,
that set.
yeah. So, so I could basically have an index, a hash index for last name and a hash index for city. But this would not be a hash index that supports non-unique keys, right? So there could be multiple, there will be multiple Jones, right? So imagine it's a hash lookup. We go one to find the first Joan, and then some sort of linked list or something like that following it to get all the other Joneses, right? And then you're thinking you then take those and you hash again for, okay, so you do a similar, so, all right, I think, let me just try to summarize what you said. So, hash index define all the Joneses. Hash index define all the Illinois. Go to bit vectors, intersect them, right? That gives you that gives you Joneses and the Illinois, and now you have a bunch of records, right? They're coming out of this, and then for each of those records, take their candidate ID and hash it into a hash table candidate ID over here. So that we find the matching rows in one step. And then that gives you the output of this thing. So what we're describing is kind of a hash kind of join as opposed to a B tree plus hash table. Right? And you're basically saying the big O is going to be the cost of the number of Joneses we find and the number of Illinoises we find, right? Okay. And so that'd be like big OM, but you also look at this and you say, well, if we're using these bitmap indexes, or these bit vector things, right? Those, when we intersect those are big O N, right? So it's kind of a goofy thing. So it'll end up looking like a big O N algorithm, right? Which seems worse than big O M, but as a practical matter, it might actually better than that. Might perform better. So I think the other way I can interpret what you're saying is that you're saying do a hash on last name, now iterate across the Joneses we find, and for every one of the Joneses we find, do a hash on for every one of the Joneses we find, go check also whether they are, we're now looking across their data, go check to see if they're also in Chicago, right? And take those, that's the case, and hash the candidate ID to find the matching geographic coordinates, right? So the downside of that is you'd be saying, okay, I find Jones really fast, but then I have to scan through all the Joneses across the country to find the ones that are involved. Okay. Do we want to continue on this, or do we want to ask different questions? Okay. Are you happy?
Yeah.
Okay. Thanks. All right. So,
This game.
trying to think of something I can say which wouldn't be too big of a hint. Sorry?
Maybe. maybe an example from relational algebra to SQL. I don't know. We don't have to on this.
You guys want to see that relational algebra to SQL, or is it sufficient that, you know, that I just showed you some pairs? Yes. All right, I'll write some relational algebra. Okay, so we'll write some generic relational algebra. Right. So if I want to say R1, R2, R3, do a natural join of these, take the output, do a theta join on R1 dot x equal R3
Could you look at
dot
that
y.
kid?
And then I want to do a selection from that to
What?
find all of these where x
Okay.
equal 10.
I'll do it.
I don't know why you took up. Talk about it later.
I might have just made a mistake.
Okay, let's turn that into SQL. Okay, so the way I would approach something like that is I'd say, I want to start at the very basis, like what am I selecting from? Right? So I'm selecting from some composition R1, R2. Right? And I'll look at this and I'll say, okay, well this is a natural join, right? So I know part of it is I want to do R1 join, or natural join, R2. And I'm going to treat that, I'm going to, just to make it easier on myself, I'm going to put a parenthesis around that. And then what's the next thing I'm doing? I'm doing a join, I'm doing a natural join, I'm doing a theta join. Okay? So that's going to join again with R3 on whatever the condition is. It's not quite right, but it's close enough. R3 dot y. So that's our condition. Now we've built that much. And then if I have a selection criteria like that, where does that fit in a select statement typically?
It's just a where clause.
Yeah, so it's a where clause. So it's a where clause, x equal 10. Okay. And what are we selecting from this? All, right? So then suppose I wrap this around and said, I'm also going to do group by y, and I want to count I want to count all the categories. How do I do that? So remember, group by has kind of two pieces. One is the aggregation, and one is the attribute list for grouping. So where's the aggregation going to fit in? So what we got here, so we'll say we're going to do count, and we're going to have y as one of the outputs. And then I also have to do the grouping, which is going to end up being below this, unfortunately. So basically right here, I'm going to write group by y. So just to kind of like go back to what I was doing is when you think about these things, don't think about them, at least I would suggest thinking about them bottom up. You have your input expression, you have your input relations, the basis of this tree is always going to be some input relations or constants. Okay? So you start with those, and you basically start at the lowest level of the tree, which is here, and you put those together. So that's how I got R1 natural join R2. Then I went to the next level of the tree, and I said, well, now I have a theta join. Then what is that? That's a join on in SQL. So we're joining with R3 on this condition. That's how I got join R3 on blah, blah, blah. Then I went up to the next level and I said, okay, now I got my selection operator. That's a where clause. So I got my where x equals n. And then in the first version we were done. We weren't doing any more grouping, so we just had select star. The next version we said, okay, we're going to group. So I'm going to group by y and I'm going to count. So I right away said the count has got to become part of this, and typically the grouping attribute comes with it as well. That's how I got select y count star. And then the actual grouping ends up being stuck at the very end. Right? So basically, group by is a little weird because the two pieces of it get split into the two ends of the query, basically. Yeah.
Okay, and could you explain like what group by means in English again?
Sure. So group by, like a grouping operator, basically says, look, I have some input relation. It's got a whole bunch of rows. And let's use y as the column, as the attribute here. So it says, find all the distinct values that y takes on. Okay? So what are they? 1, 2, 3, and 1 happens again, 5, 9, 3, 1, 1. So those are the unique values. And then it says, for each one of those, grab the rows that have those values and assemble them there, right? So we just took 1 and we said it's these rows. And 2, right, would assemble just this row. And then 3 would assemble this row and this row. And what else we got? 5. There's 1 row. And then what else are we missing? 9. So 9 has 2 rows. Right? So you kind of imagine that we're just now, another way to think about it is that we're taking this table and we're sorting it by this value. And then we're looking at every contiguous block, right? So we're going to have 1, 1, 1, 1. Those are going to be assembled together 2, 3 to 5 to 9s, right? If we sorted it, we get the same effect. So that's the grouping part, okay? And the aggregation part is all about how you take these things in a group and generate 1 row about it. So the idea is for every group that's defined here, we're going to have 1 row. Okay, so that means in the case of this 1, we need to flatten these 4 rows into 1 alpha row. With this 3 over here, we need to flatten these 2 alpha rows, these 2 rows into 1 alpha row. And the aggregation function tells us how to do that flat. Okay, so here we're saying count is our aggregation. So this is going to flatten into 4, right? So there's 4 of them. This will flatten into 1. This will flatten into 2. There's 2 of them. This will flatten into 1. And this one will flatten into 2. And then that is our output relation for the group.
Do they always have to have an aggregation?
Yes. Yes. You have to find some way to flatten multiple rows. Like here's a practical example. I tell you, okay, we have a big company, and there's always different categories of employees. There's 150 categories of employees. Each category has some random number of employees in it, right? You know, like professor, IT staff member, TA, whatever, these are all categories, right? And then I ask you a question like, for every category of employee, what's their average salary? Okay, so what am I asking you to do? I'm asking you to make me a table which has got category salary, TA this much, professor that much, IT staff guy that much, right? Average, right? And what it would mean is exactly this. It would mean find all the categories, TA, professor, staff worker, etc. Collect together all the ones that are the same, all the professors, all the TAs, all the IT staff, right? And then summarize somehow. And the summary here would be an average, right? So instead of counting, you say, what is the average salary? Okay? And, I could go fancier. I could say, well, is there any job category, finally, for every job category, tell me the difference in average salary between people who have 5 years of experience versus people who have 10 years of experience. Right? So that would look something like grouping by two things, category and years of experience. Right? And then I'd have an output table which would say, TA, less than 5 years of experience, this much money. More than 10 years, that much money. And if I wanted to, I could then feed that into another query, which would say, okay, show me the categories sorted by the greatest disparity between the greatest percent disparity between 5 years versus 10 years. So queries like that, where you're trying to summarize stuff. Yeah, that's the main thing I should probably get across here. So group by aggregation, etc. It's all about summarizing data. The vast majority of use cases are how do I summarize a huge amount of data. Okay. Other questions?
This is unrelated to relational algebra, but I have a question. Just display or extendable hashing and linear hashing.
Okay. Yes. So I'm going to go. I'll go over extended. So I'm going to. Why do we care? First of all. So a little bit about how extendable hashing works. I'm not going to go and describe linear hashing, but I want you to know the attributes. Okay. So the problem, if you have a hash table of any kind, okay, the problem is that once it gets too full, you start having lots of fields, right? So one way of dealing with collisions is you chain, right? But that sucks because it basically says your big O1 hash table basically is working at the speed of the chain, okay? So the other alternative is you make the hash table bigger. Right? So if you start to have a lot of collisions, maybe you double the size of the hash table, and now you have fewer collisions. Okay? So this idea of like doubling the size of the hash table in response to too many collisions, or doubling it in order to grow, or halving it in order to shrink. So that's extensive hash. Right? The problem with that, because and I'll diagram how it works in a second, but the problem is that it is asking you to always expand and shrink by powers of 2, right? Double or half. Which doesn't matter when you're talking about, like the hash table is tiny and you double its size, it's still tiny, right? The increment, the addition you have to provide is, the additional space you're going to use is tiny. But if you double it, if it's huge to begin with, like if it's say 10 gigabytes in size and you double it 20 gigabytes, right? Your cost is 10 gigabytes, right? That's a huge commitment. If you double it again, your cost is going to be 20 gigabytes, which is a huge commitment. Okay? So what linear hashing does, which is a lot harder to implement, but what linear hashing does, it allows you to grow kind of, instead of doubling, it allows you to grow incrementally. It allows you to say, I want to increase my hash table by, I'm at 10 gigabytes, I want to increase it to 11 gigabytes. can do. I'm at 20 gigabytes, I want to increase to 21. Can do. I'm at 40 gigabytes, I want to increase to 41. Can do. Right? I can't do that with extensible hashing. So the way extensible hashing essentially works is that you make use of the bits in the hash function. So abstractly of a key, it's going to a hash function. The hash function is producing some number of bits. Let's say a large number, just for the sake of argument, 256 bits or something. Fives here and zeros here. So now the idea is you make use of only a fixed number of bits. So when you start off with your hash table, you basically make use of, say, none of the bits. Right? I'm going to start differently than I started the class. So let's suppose you say, I'm just going to completely ignore. I'm going to completely ignore this. Actually, I'm going to start with this. I'm going to start off by saying my hash table has 2 buckets. Okay, bucket 0 and bucket 1. And here in this world, these are going to be disk blocks, so we can store lots of keys in them. Right? In a classic 214 world or 211 world, each bucket has 1 thing in it. Okay? How do I decide whether you're going to 0 or 1? I look at this top bit. Okay? So if I'm going, if the top bit is 0 for the thing I'm hashing, I'm going to put it here. If the top bit is 1, I'm putting it here. And I keep doing that, doing insertions, etc., until I have collisions, until I run out of space. Okay? So I start filling these things, and if the hash table is any good, I'm going to fill them pretty much at random for every new key. And so they're going to grow pretty much the same in size. But eventually, one of these 2 halves is going to, run out of space. At which point, I make a new generation of this hash table. Okay? And the new generation, instead of having 2 buckets, it's going to double the number of buckets. And now I'm going to call them 0, 0, 0, 1, 1, 0, and 1. And conceptually, there's an optimization for this, but conceptually what I can imagine doing is I now take everything I had in the original, and I go back and look at their hash function. Instead of using the top bit, I use the top 2 bits. Okay? So that means the keys that are in here are going to get distributed among those 2. So if this is full, each of these will end up being half full. Okay? And this is top bit is 1, so their keys are going to be equally distributed among these 2. Half full. Okay? And then I keep inserting, and eventually one of these is going to get full. And then I play the same game. Okay? And the optimization is that I can basically decide that this block is going to become that block, for example. So I only have to move half of it. And I can say this block becomes that block. And so I only have to move half of these. Right, so that's extensible hashing when you're growing. And when you're shrinking, we basically say, when you know that all the buckets are less than half full, right? Then what you can do is rehash and only use the top bit again, and you know they'll fit into this, right? So the size of this thing is going to be, they use top bit 2, they use top 2 bits 4, they use top 3 bits 8, etc. And that's where that exponential expansion comes from.
Before the expansion, like the book talked about like this idea of a global and a local index, whereas like in your second hash you have 2 bits, but then you also have basically something similar to like chaining where it essentially goes to another set of blocks, and that block has a local index of 1 bit.
Yeah.
Yeah. yeah, it's like, how exactly does that work?
I think you're talking about the linear hashing part, to be honest. But yeah, I mean, I will say this. I mean, so if you think about chaining hashes, you can still have chaining hashes in this world. Because all you do is you basically say, I'm going to pretend that one of the entries in this block is basically a pointer to a chain block. Okay? And then if I have a collision, I go into this block, and I don't have room in this block, I can follow the linked list and put it here. Right? And if this one gets full, I can have another chain block, etc. And just like with chaining hashes in memory, eventually this gets too long. That starts to be a problem. Right? And all I'm saying is that you can also think about, I mean, the key thing for extensible hashing anyway, the key thing is this notion of like this doubling of the sort of base table, right? That you can achieve by using more bits, right? And the linear chain here, I mean, as a practical matter, yeah, you probably do something like this because see, another problem with like when I grow this is that I'm going to end up having when I grow this, I'm going to end up having to do a lot of movements, right? And potentially I can do fewer movements if when I start chaining, I drop stuff into this chain according to the next step. There's one optimization. What else do I want to say about this? So I mean, just like with in memory, this could be a tree as well, right? So you could basically say when I chain, I end up decaying into log cost, log n cost lookup as opposed to linear time lookup. There's all sorts of optimizations like that. Yeah, is that kind of?
Yeah. And so for like hash tables like main memory, there's always the load factor, which is like telling you essentially the double. Is there something similar with here, like with blocks, or is it just over the doubles?
There is a load factor. So basically, this is a little bit similar to. So basically, everything you learn about main memory applies here as well. Is the main thing I want to get across. And what is the purpose of the load factor in main memory?
I mean, I would say to dynamically increase the size without it having to without filling it in advance, I guess.
Yeah. So basically, you're saying I want to keep. So load factor is saying something like I want to keep it X% full, right? Below X% full. So once it gets beyond X% full, expand. And the example I was given here is like, that threshold is 100%, right? But it doesn't have to. I mean, the problem making it 100%, and this is a little bit like the B-tree leaf thing, or the B-tree node thing, right? In class I was like, well, you probably want to keep it between 2/3 and 1/2 full. You want to keep the load factor within these two bounds. You could set the load factor to 100%, right? I mean, it would still work. But by setting the threshold a bit lower than 100%, and also by having these two thresholds, you basically reduce the number of times that you basically do an expansion very quickly followed by contraction. Right? So the expansions and contractions are the killers in terms of performance. So one of the purposes of load factors is to basically avoid oscillation in the system, where it's like a bad case would be somebody gives you a sequence of requests, like insert, delete, insert, delete, insert, delete, insert, delete, right? So if you just have like one threshold for that, right? What's the bad case that could happen in B-tree? It could be split, 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 merge, 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 split, 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 merge, 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 merge. What's the bad case that could happen here? It could be copy everything, copy everything? Copy everything on every answer you delete. Right? So these things like load factors and these thresholds are basically knobs in the system to get the average case to get the worst cases to behave a little bit more than the average case. Okay, other questions?
So will you have that problem any time that your low threshold and your high threshold is 2 times the low?
So again, if the high threshold
If
is,
the high is 2 times the low, like 1/2 to 1 or 1/3 to 2/3, because then if you say it was 1/2 and 1, you add 1 and it's full, and then it splits, and then you delete 1, it doesn't have to like go back.
yeah, but by having the threshold separate, so I'm saying merge when we split, okay. Yes. Okay, so actually you probably don't want the thresholds to be 1/3, 2/3. And that, what I'm getting at. What would be ideal? So I'm not sure I can answer this online, but I guess the question would be like, what would be an ideal threshold?
2/3 and full.
Sorry?
2/3 and full.
You want 2/3 and full?
That's how we do a lot of cases.
Okay.
Wait, 2 times full, is that impossible because
So you shrink less, or you expand, what was it? It was 2/3. There's like a 2 weeks in each 336 dollars. So, I forget exactly what it is offhand. I know that the best load factor is 2/3, but you can find the right load factor and prove that it's the right load factor.
You're talking about the load factor for
So this is for arrays,
Yeah,
but
for
it can generalize pretty well. But it's like a serious field of, or at least was a serious field of research. So it's hard to summarize in like a 10-minute discussion.
Yeah, so, and I'm not, I mean, that's a good question. I'm not gonna ask you to come up with the right load factor on an exam or something like that. And as Mike is saying, this is also, so when you take algorithms, one of the things you'll learn about is amortized analysis. And the sort of, figuring out what the right load factor is for hashing is an example of an amortized analysis problem, right? So we'll leave it at that for today, okay? Any questions? Going once, going twice. Okay. Good luck on the D2 lab.